Hey everyone, my name is Quentin. I used to work in a mid-sized tech company deploying their AI infrastructure. So about 6 months ago, I wrote this article called You Suck at Deploying AI Models, and it was kind of a rant slash response to a lot of the inefficiencies that I was seeing in sort of the companies that I was working at. I made this post a couple of times on Threads, and I can see right now this is the second time I posted it. It's at almost 11,000 views right now. So this seems to be something that a lot of people are resonating with. And so I thought I'd make a video on it. So without further ado, you suck at deploying AI models. If I had more time, I would have written a longer rant. Some dude. If you deploy AI models to production, you need to give a shit. Please, I beg of you, stop wasting the compute, stop over provisioning extremely expensive GPU nodes, stop wasting our time, stop wasting my time, and stop throwing money into a furnace. I just found out that GPU utilization can be at 100% while doing zero actual work. This confirms a long-standing theory I've had that streaming multiprocessors play a much bigger part in AI inference than most people realize, and just relying on VRAM and GPU utilization as your sole metrics is worse than useless. It's misleading. It makes you think that everything is all hunky-dory when in reality, you are probably only using 10% of the compute you are paying for. Fun fact, that's based on a true story. And tell you what, when you're only actually using 10% of the compute, when you're paying nearly 100 grand per month for GPU nodes, that's not a great feeling. Moving on. I paid for the whole computer. I'm going to use the whole computer. When you are deploying LLMs to production, this is your North Star, your guiding light, your mantra. Provisioning GPU nodes on AWS runs hundreds of dollars per node per month for a small one and thousands of dollars per month for larger nodes. Just a note I want to make here is that if you're working with something like BERT, like classification models, usually you can get away with like smaller models. But if you're going for something closer to like state of the art image generation or actual large language models in the I'd say probably about 32 billion parameters and above, non-quantized, of course. Usually, though, that's when you're going to start running into the thousands of dollars per month. LLM model deployment is the art of pegging every single resource on that box as close to 100% as you can to maximize the amount of useful work you can get out of it. Using GPU resources efficiently matters. Failure to understand the underlying architecture is lighting money on fire, and a lot of it. Okay, I want to talk about this for just a little bit. In business, sort of broadly speaking, you're going to have two different ways to approach problems, and both have legitimate applications in different kinds of scenarios. Some things are going to be engineering problems, some things are going to be business problems. If you are a smaller company and you need a lot of data, you want to train your own model, you could take the time to write up a scraper or spin up a whole bunch of Docker instances, connect it all up to Kubernetes, and scrape the internet from scratch. Doesn't that sound like fun? Another way that you could approach this problem is you could just buy data, and then boom, your problem goes away. That is a business solution to a business problem. I don't know where the line is, where the lines, it's a bit of a blurry line between what counts as an engineering decision and a business decision, but there is a difference between the two. An engineering decision, on the other hand, is something like what we just saw with DeepSeek over the last couple of weeks. I had my suspicions for I'd say about a year or two prior to this point. We as an industry were severely underutilizing the hardware that we have available to us. Most of the general, I guess, programming population has had access to like CPUs and RAM, that kind of stuff. They've been able to tinker with it for so many years, but we've never really had a good reason to dig that far down, that many people digging that far down into the assembly level, into GPUs, because there's just never really been that big of a need for it before AI, I should say. back when games started, like in the mid 90s, back when video games started to take off a little bit and people were experimenting with it, that's when you had to really come out with some really interesting tricks. Maybe I'll do a video on some of the stuff from back then. But you really had to sort of pull out all the stops to really get the hardware to do what you needed it to do. But ever since the hardware has gotten better, like say in the 2000s or so, 2000s, 2010s, there hasn't really been a need to dig that far down with GPUs for the vast majority of the programming industry. Deploying LLMs and getting them to run extremely efficiently is not a business problem. It's not something you can buy. It is something that needs to be invented, created, engineered, and deployed. You can't buy it. At some point within this domain specifically, you cannot just pay for more servers. The expense will outweigh any revenue that you bring in. You need to engineer a more efficient solution. That is an engineering problem that can only be solved with an engineering solution. You cannot buy your way out of that pit. Going back to the article, LLM deployment pushes the bounds of what computers are capable of. You cannot ignore your computer system's limitations like you can with normal software. Okay, well, we're only 2 sentences back into it, but I'm going to go on another little bit of a relative tangent. So I used to work with IoT stuff. And the way I see it is that on one hand, you've got AI. On the other hand, you've got IoT. IoT is very, very hardware constrained. You know, the people working in IoT, they need to be efficient because they don't have enough hardware to really do a lot of the things that we kind of take advantage of in the web development world. On the other hand, you've got AI, where the software is just so intense, it requires so many resources that you kind of have to go back to the mentality of IoT. You need to learn how to be efficient in this domain. In the middle, you know, there's running a web server is not intense, and the hardware to run a web server is so powerful nowadays that people don't need to think about it. In these two domains, these are the extremes. You need to think about it. Most people deploy an LLM to a web server using something like Hugging Face and FastAPI and call it a day. This is just fine if you have virtually no users and don't expect redundancy. But if you're building something serious, you cannot just be content with that. Deploying AI models is a minefield, so let me kickstart your journey by offering you some questions to ask yourself as you improve your API. How do you set up redundancy? How are requests routed between instances of the model? How many models can you load simultaneously? Can you load multiple models per Docker container, or do you need to split them out? Oh, by the way, what is the resource usage of those models based on those different kinds of configurations? If you have 8 gigabytes of VRAM and your AI model takes up 2 gigabytes of VRAM, if you're able to load, say, 2 models in there at a time, there's only so much processing power that the GPU is going to be able to handle. And so it's not going to be able to run at 100% for both loaded models at the same time. Where is the breakpoint there? Do you know? Can multiple Docker containers reserve the same GPU? What about in Kubernetes? That's a fun one because in some versions of Kubernetes, you can't. I found out after I wrote this and after experimenting with it quite a bit that I was able to in specific versions of Kubernetes. It's been so long since I've worked on it, I don't remember the exact details of it, but that's landmine that you got to look out for. Do you need a GPU base image? No, you don't. Why does PyTorch come with CUDA? Why doesn't it just use the CUDA on your system or the CUDA that might come with any base image that you might be using? I do find it to be convenient. However, if you have a host machine with CUDA installed, a base image with another version of CUDA installed, and the PyTorch version of CUDA installed, which does the model use? The more instances of CUDA that you have installed in various parts of your CI/CD pipeline, the slower that's going to be and the worse your development experience is going to be. And that also just means that there's extra cruft in your CI/CD pipeline, in your application, in production that just doesn't need to be there. It's not just, oh yeah, whatever, we're not going to look at it. No. When something goes wrong, and something will go wrong because this is not a domain that is fully fleshed out at all. When something goes wrong, you're going to have extra things that do not need to be there that are suddenly there that you're focusing on that you need to fix. That's going to be a massive headache. It's going to slow things down. It's not going to be a good time. How do you quickly load data onto and off of the GPU? What is the relationship between latency of loading info onto the GPU and processing time on the GPU? How does this change as batch/message size changes? What is the time to first token and how do you speed it up? How does the model parameter precision level affect the loading speed, inference speed, quality of inference, disk space, and space in VRAM? Specifically, using calculated numbers, not in a kind of hand-wavy way where it's like, oh yeah, if you quantize it, it makes it faster and it takes less VRAM. How much? How much? We have the parameters. We have the precision level of all of the parameters. We have all the layers. This is all assuming that you are using like an open source LLM. We have the GPUs. We know what GPUs are on the AWS instances or whatever cloud instance that you're using. We know the precision level that the GPUs can use. We know the clock speed. We know the SM clock speed. We know all of the specs of the GPU. All of this should be calculable. There should be no guessing when you put an AI model into production. There just shouldn't. And if you think it's okay to just guess and check with something like this, you are a lazy dev. You are lazy. I don't respect that. How do you calculate VRAM usage and inference speed based on the properties of the model and GPU? How does inferencing with a small batch compare to a large one? Does the GPU usage spike to 100% or does it only use a fraction of it? This is a fun one. How is GPU utilization actually calculated? Hint. It isn't real! It's an estimate based on many different factors. If you want a real good rabbit hole to go down, learn about GPU architecture. Learn about how it's actually built and designed. Take a look at Modal's GPU glossary. Basically, one of the guys that works at Modal got similarly frustrated as me that the information around how GPUs actually work, like GPUs, CUDA, all this other stuff, was just so scattered around the web that he just decided to say, screw it, I'm sick of not knowing how this works. And he built this really cool online resource that just kind of goes over in detail how all of the different levels of the stack for GPUs connect together. Link for that will be in the description down below. What is the role of streaming multiprocessors? How long does it take to unload a batch from the GPU? Is there a way to speed that up? If you've been taking a look at any of the stuff that DeepSeek has been releasing over the last week, you'll know that, yeah, there is a way to speed it up by quite a lot. Why do tried and true tools like NVTop aggregate information rather than showing the direct number? Here's the thing. If I'm trying to learn more about the hardware that I'm running AI models on, I want to know as much about that hardware as I possibly can to optimize the ever-living snot out of any kind of inference model. NVTop doesn't do that. I believe it's something like 6 times a second or 10 times a second that it aggregates information. Well, if you're working in a system where you have tens of thousands of messages coming in every single second and hitting your server, just it's going to be going faster than 6 times a second. You're going to want to see higher fidelity information so you know exactly where in your pipeline you can optimize things. And I don't think you can get that with NVTop, at least from the research that I've done. Why does NVIDIA SMI lie about the version of CUDA installed? That's a fun one. What version of CUDA is your special snowflake of an AI inference engine compatible with? Oh, man, that was annoying. So you got a couple of them. You've got VLLM. It starts with an S. Hang on a second. I'm going to find this for you. Okay, here we go. Yep, VLLM. You've got Ollama, Llama CPP, SGLang, Triton. I don't know what TGI is. I've heard of TensorRT. You've got Hugging Face. I think they have a built-in serving solution. There's a lot of options, and this isn't a complaint against the maintainers of these open source repos at all. Genuinely, thank you for all of the hard work that you guys are doing. But if you're trying to deploy an LLM onto your own hardware and you don't want to go bankrupt, and you want your users to have a great experience, you need to understand the differences between all of these different serving solutions, because some of them are optimized for different kinds of situations. Some of them are only compatible with certain formats like Onyx, Safe Tensors. I think those are kind of the main ones. Pickle has kind of gone out of style for a few years now, but depending on the format, that will kind of determine what sort of deployment infrastructure you're actually able to utilize. Hello, Editing Quinton here from a day later. The inferencing engine that you use will mostly be determined by your use case, not necessarily the format. Onyx and Safe Tensors and a lot of the other common ones are usually going to be covered by most, if not all, of the common inference engines. Why can't multiple child processes inference with the same model? Okay, so this one. I ran into an issue at one point when I was working in a tech company where if you have CUDA that reserves, kind of via PyTorch, reserves the GPU in a parent process, and then that parent process tries to fork, it will break. As in, it just will not boot up the server at all. You'll get, I think it's CUDA error 3 or something like that. It's a hairy, tangled mess. Ugh. How does interconnect affect efficiency? How does PCIe bandwidth affect efficiency for multi-GPU inference? Does your CPU even have enough PCI lanes available? Do you even know what PCIe lanes are? If you're dealing with AI inference infrastructure, you darn well better know what PCIe lanes are. How does the amount of CUDA cores affect the speed of inference? Why is a $1,500 consumer-grade graphics card faster at inferencing a model than a $380,000 enterprise server? This is the only question that I am not 100% certain on myself. In the past, I have found that gaming GPUs inference faster than the GPUs that you're going to find inside of cloud data centers. And that's largely because the clock speed is actually going to be faster in a gaming GPU than in an enterprise AI GPU. They'll advertise it as being optimized for AI. Those cards are actually optimized for efficiency, low energy usage to performance, because believe it or not, it's very expensive to run enterprise GPU cloud infrastructure. How do you prevent memory leaks from happening when the batches are taking too long to process? Each one of these is its own rabbit hole. I'm just going to skip over some of the little side tangents and explanations just because I would be here forever otherwise. How do cards with versus without tensor cores affect the speed of models? And more importantly, why? How is the difference calculable between different GPU types? Because remember, you should be able to calculate these things. How do you do continuous batching? What about streaming responses? Is your model type compatible with the engine you want to use? What about the inference mode? How is encoding versus decoding done on the GPU, and how can it be optimized in a cluster? What parts of my specific model architecture could be improved by writing a custom CUDA kernel? How does all of the above affect training versus inference? This field is so far from standardized. The ground is shifting beneath our feet as we build, and failure to understand your tools will result in a half-baked implementation that will waste tons of time and money. The reason I'm so obsessed with pushing LLMs to their limit is because of all the waste I've seen in the industry due to lack of knowledge and, worse, lack of caring. So many people just not caring that the AWS bill is ballooning in ways that dwarf all other team spend. You don't need to know the answer to all these questions. I don't know the answers to all of them myself. You can pretend they don't exist, but you will be subjected to their limiting effects nonetheless. Hope you enjoyed.